Hey everybody, and welcome back to NTRAS. We're going to do our first kind of informational video here on our CCNA series. Now keep in mind, this is more of a fundamentals video, and I've changed around the design of my PowerPoint slides a little bit, so let me know if you like it, don't like it, love it, or hate it, because I'm kind of at odds. I really liked the way the new one looks better because it's more of a contrast. You know, in the last video I was thinking about doing, it was a really light blue with white lettering, so I don't know if it looked all that well, but hey, let's get to it and see how we like it. One of the things we do have to think about, fundamentals. Without fundamentals, we'd be lost, of course. Without routers, we would never get anywhere. One of the things you need to think about when you're learning to be a network engineer is what is a router technically versus what is a router actually. So if you want the technical argument, well, a router is a router. That's really all it's supposed to do is route. It's got physical interfaces, it does routing, VPNs, that's kind of it. When you think about it from an actuality standpoint, well, all devices, network devices at least, do one form of routing or another. Now, actuality router is a layer 3 router, so it routes IP addresses. And almost, 95 or more % of Cisco switches out there are layer 3 capable. I mean, there are some that are not, like the 2960CX was not a layer 3 switch. So maybe you can't consider that a router, but the 3560CX, the 9300s, most all of the switches have the ability to do some form of routing. I mean, even a lot of the switches have the ability to do VPNs. You might not have encryption, but it's still a VPN. So take with a grain of salt, a router versus a switch versus a firewall. A lot of the times they're all kind of equal, depending on, of course, what you need in your environment. So once again, here's our introduction. We have ntras.com and cisco.com listed here. This is where you can go to get the exam topics, and we'll be actually starting on those after this video. But as the introduction continues, we have to talk about our network fundamentals. We are going to be talking about routers. Those allow us to, of course, segment a network. Once again, layer 3 switch can do the same thing. Of course, switches let us connect many devices. One of the things you do need to realize, however, is there are switch modules that can go into routers. So it's kind of an if and give and take here. A Cisco ISR 1000 has built-in switch ports. An ISR 4000 has the ability to install little switch port NIM modules, or the big software modules that's an actual switch itself that you install into a router. So we do have some of those capabilities with the route and switch environment. Now when we move on to firewalls and IPS, well, once again, how are we going to protect the network? In Cisco's case, we're going to be looking at the ASA and the Cisco Firepower appliance. Keep in mind, however, that you can technically turn a router into a firewall and potentially an IPS, or an intrusion prevention system, with the right software or hardware modules. So keep that in mind. There's a lot of different things you can do depending on the platform you have, or of course what you buy. Now these days, you could probably go out and get yourself a, what do you think, a Cisco Firepower 1010. The Cisco Firepower 1010 allows routing, switching, and firewall and IPS all in the same box. So one device can do a lot of different things depending on how large your environment is, whether it is your house, buy yourself a Firepower 1010, connect that into your ISP, and then you can connect your computers and wireless access points directly into that firewall, and you have a network with one device. course, that leads us on to access points. The access points, of course, allow us to connect to our 802.11 wireless network, or Wi-Fi. Controllers, on the other hand, are basically devices that allow us to manage other devices over the network. So like a Cisco access point can be autonomous or it can be managed. So the Cisco Wireless LAN Controller, or WLC, is the controller that manages the access points. We also have some other things, as you see on the screen here, such as DNA Center and Wireless LAN. But when it comes to controllers, we also have controllers such as SD-WAN controllers and Cisco ACI for, of course, software-defined wide area networks, and of course ACI, which is basically Cisco's software-defined data center. Then we talk about endpoints. Well, you're probably sitting in front of one right now. If you're looking on your phone, well, this is an endpoint. If you have a laptop in front of you, if you have a computer in front of you, if you have an IP phone, like I have one right down here, all of these things are considered endpoints because they go onto the network, either wired or wireless. They get an IP address, and they have a MAC address, and they use all of the layers we're going to be talking about in just one moment. Lastly, of course, we have our servers that, well, pretty much go anywhere. But technically, servers are meant for the data center, which might be off somewhere else, off campus, or in a specific room in one of your buildings, etc. But anyway, the switches allow us to get from the computer onto the network. The router allows us to connect to different networks wherever they may be. So I live in Las Vegas, so my house is just down the street from Switch, which is a huge data center. And without my routers, well, I wouldn't be able to get to my data center because, well, IP routing is how we get everywhere. We'll talk about that in just a minute with the OSI model. But that brings up the question, how networks function. The reason I bring up the OSI model made by ISO, is because starting out, and a lot of old-timey network engineers like myself in an interview would be like, okay, do you know what the OSI model is? Do you know all the layers? And do you know what its use is, basically? So running through it, we have 7 layers: physical, data link, network, transport, session, presentation, and application. As in the 7 layers of how communication works. Physical, of course, is based on the physical properties of the network interfaces. So once again, if you look at your phone, well, it doesn't actually plug into the network, right? Physically, there's a little chip on this phone that connects to an antenna. And that antenna would connect either to the cellular network or to your Wi-Fi. That would be the physical connection to the network. On top of that, we have the data link layer, which uses 2 separate protocols to allow communication at layer 2. However, we'll see a little later on that we're going to focus on the MAC address in frame transmission. Layer 3 is the network, where we talk about IP addresses on the devices, and those transmit in the form of packets. The transport layer is where the application's port comes into play. So as an example, HTTPS, or secure web browsing, is over TCP port 443, just as an example. Transport layer works in segments. So the first thing you might be able to see here is transport, network, and data link, or SPF. Segments, packets, frames. That is a good mnemonic that I've used, and we'll talk about that a little bit in the next slide. Mnemonic devices can allow us to remember things. SPF, that's suntan lotion. Segments, packets, frames, layers 4, 3, and 2. Next we have session, which controls the connection between 2 devices. Of course, as it says, 2 computers or devices need to communicate. It creates a communication session between them. Next, we have presentation, basically how applications are encoded and the syntax used to present an application to the session and allow computers to be able to understand what that application is trying to provide. The application layer is basically the application that the user uses. So I may be using PowerPoint and that's my application, but not necessarily the application the computer's using, so it can be a little bit confusing there. However, this PowerPoint is an application that creates what we see, and then every other layer allows us to view and transport this presentation from me to you. Layers 1 through 7, 7 to 1. In learning mnemonic devices, I have this slide here. So don't worry too much about that header there, that's just filler. But there are many occasions where you may be asked about the OSI model, as I mentioned, especially in network interviews. So if you were to come to me and say, I want to be a junior network administrator, I would be, okay, do you know your OSI model? Do you know the difference between layers 1 through 4? Typically, if you can answer those couple questions, well, layer 1 is physical, how it connects to a network. 2 is data link based on MAC address. Layer 3 is network based on IP address. And layer 4 is the application port number. And they use segments, packets, and frames. Great answer. It would get me to stay in that interview. So the way I learned it about 20 years ago, please do not throw sausage pizza away. Physical, data link, network, transport, session, presentation, application. All people seem to need data processing. Application, presentation, session, transport, network, data link, and physical. So mnemonic devices are a really good way of learning, and it's how I learn, if you couldn't tell from SPF and these two. So remembering the layers and understanding can break the interview, as I mentioned. But here is another mnemonic device that I use to remember my BGP path selection. We love all our mothers, even in older relationships. So with BGP, we have to go through a selection process. Weight, local preference, locally originated, AS path, origin type, and MED. Those are the ones you really need to know. But on top of that, we have eBGP learned over iBGP learned, the IGP metric, the oldest learned route, and of course the router identifier. So a mnemonic device allows me to remember this, even 10 years later. We love all our mothers, and I can word it out. Just keep in mind there's a couple more to the BGP path selection. It's not 100% complete. There are some more, so don't get mad at me for that. This is the fundamentals, of course. So starting out and looking at the physical layer, we're going to look at a few different connection types. Now, once again, just fundamentals. You may ask yourself, how can I connect my computers or servers into the network? Now, if you watch my home lab, you're going to notice the 3560 has mostly copper ports, but it had SFP ports in the end, which basically allows the use of a transceiver. A transceiver can be copper or fiber and can go all the way up to 25 gigabits per second. Now, the reason I mention that is because the QSFP is larger than an SFP, and you can't put the QSFP in an SFP port. So something to remember. And as I mentioned, we have RJ45 copper, which is what all of our computers pretty much connect to. And then we have the 1 gigabits per second SFP. For RJ45, we can also have what's called a multi-gigabit connection. One of the great things about copper is you can actually negotiate between 1 gig and, in this example, 10 gig. So my computer actually has a 2.5 gigabit connection NIC. However, I'm plugged into a 1 gigabit per second connection switch. And that's kind of what they mean by multi-gigabit. So you have the ability to go from 1 to 2.5 to 5 to 10 gig, etc. Now when it comes to the SFP Plus ports, it is still an SFP, except it has been modified to accept 10 gig and 25 gig connectivity. So you'll also see here, along with the SFP Plus, a 10 gig twin-ax and a 10 gig AOC. Technically, these are also SFP Plus ports. However, the transceiver and the cable are one device. In an SFP Plus port and SFP port, you have the transceiver that goes into the device, and then a standalone cable that you plug into said device. So those are copper SFP RJ45s. We have the 40 gig QSFP Plus and the 10 gig QSFP Plus. So kind of a little backstory on that. The small form factor pluggable is basically a smaller version of what we used to use that was called a GBIC, or basically a gigabit interface connector. And they're old. A lot of people will call them mini GBICs, but they're technically SFPs. So that small form factor pluggable, 1 gig, 10 gig, 25 gig. What you're going to notice about the QSFP Plus is it means quad. And the reason it means quad is because, well, QSFP Plus is for 10 gig. The 100 gig QSFP Plus is for 25 gig connectors. So keep that in mind when you're talking about the transceivers versus the cables and whatnot. Now there is a lot more to talk about when it comes to optical media standards like OM3, OM4, and OM5. Pardon me. But not really necessary right now. Other things you have to worry about is something called a digital subscriber line. So somewhere in your house there's a 2-wire phone line. You probably don't have phones the way, traditionally we've had them, but an RJ11 is a connection from a DS0 back to whoever, like AT&T, and it plugs into your physical landline. I mean, I have a VoIP phone sitting here that uses RJ45. But originally, it was an RJ11 that connected into the wall and connected back to whichever service provider you had. That is a DS0, accounts for a single voice call. A DS1 is basically a bundling of, I believe, 24 DS0s, with one being a like a signal channel. A T1 and a DS1 are kind of used interchangeably. There's also an E1, which is the European standard for a T1. Slightly different, slightly faster. To be honest, I don't know why we don't use E1s, but we have to be different, right? And then, of course, we have the DS3 or T3 lines that allow for about 45 megabits per second and consists of 28 DS1s. Yeah, so keep that in mind. A DS0 is 64K, a DS1 is 1.544 megabits per second, and a DS3 or T3 is about 45 megabits per second. So really old stuff, but can still be good stuff. The other thing we have to talk about is fiber connectivity when it comes to the fiber channel protocol. Now, the fiber connectivity for fiber channel has its own dedicated storage network. It's easy to get them confused, but they still use the same SFP Plus style connectivity and the ohm style cables, even though one's using Ethernet, one using fiber channel. We need to be aware of the connectivity between network devices such as switch to switch, switch to router, switch or router to a firewall, and of course router to router. Now, a lot of different devices have a lot of different connectivity options. So a Cisco ISR 1111 has, what would it be, 2 RJ45 copper layer 3 ports and a single SFP port that is shared with one of the copper ports. So technically it has 2 ports, but you can use either the copper or fiber connectivity depending on what you need it for. The ISR 4000 series has technically 8 ports, but you can only use 4 of them. So it has 4 copper ports and 4 SFP ports. You just have to choose between copper or fiber depending on which one you need. When it comes to switches, well, Cisco 9300 series, they have both all copper ports and all fiber ports. However, on the modular line and the static line, of course, they have ports that you can use on the end, which are technically uplink ports, but you don't have to use them for uplink. You can use them for fiber connectivity, such as 1 gig and 10 gig, and I believe they even go to 40 gig, if I'm not mistaken, that goes from your IDF to your MDF. Basically, your intermediate closet where you'd have all of your end users, all of their cables connect into an IDF. Especially if you have multiple IDFs, they'll all connect back to a single main distribution center where they can all come together. So IDF and MDF. Once again, the Cisco Firepower 1010 appliances are 100% copper. I believe on the 1120 you do have SFP ports, so you can run fiber. And if I'm not mistaken, it's on the 1140 series where you finally get 10 gig SFP plus connectivity on those Firepower devices. So when you're designing out a network and wanting to understand speeds, well, what devices do you have? What devices do you need based on your overall speed requirements and things like oversubscription? There's other things too, the Cisco Catalyst versus Cisco Nexus switches. A lot of those are basically the same, they're just running a different OS. So you can choose copper uplinks for your servers, SFP, SFP Plus, and QSFP Plus for your servers, or a mix of all 3 depending on what you need your environment to use. Let's see, connectivity between network devices and storage devices. We talked about this earlier. Keep in mind that fiber channel for storage is a lot different than Ethernet for network and storage. So the cards you buy for fiber channel are going to be dedicated to fiber channel only. The Ethernet adapters, well, you can actually get a few different ones of those. They have just plain old Ethernet. That's all you can do. Then they have iSCSI hardware. So you can actually run iSCSI. Basically, it's fiber channel light, so to speak. It's called a converged network where you can run data and storage over the same lossless Ethernet network. So when you're designing out how you want your network to function, these are a lot of questions you have to keep in mind. Do I have local storage? Do I have remote shared storage? Well, how am I connecting to that shared storage? Do I have a hyper-converged environment where I'm sending out 3 copies of my data every time I have something written? So there's a lot of questions you may have there. As I mentioned, the Cisco Nexus line is for the storage network virtualization, but you must also understand the Cisco MDS, where it uses pure storage connectivity. A lot of the times the MDS has fiber channel and virtual fiber channel, which is basically fiber channel over Ethernet, as I mentioned before. So even though you might have storage going over your Ethernet, if it's not iSCSI or NFS, you might be using the actual fiber channel protocol over a lossless Ethernet frame. So there is a lot to be aware of there as well. As you might have quite understood the fact that the CCNPs, well, there's quite a few of them, so there's a lot of information, and depending on where you want to specialize, currently we're focusing on the route switch side and delving into other stuff, so that will probably be our first route. Layer 1, the physical layer. Also keep in mind with the physical layer, there may be design requirements that software or organizational requirements, as I mentioned, storage requirements, and even personal preference can come into play when dealing with the physical layer. Once again, if you're working with a guy who loves fiber channel and loves a dedicated storage network, well, they'll probably want to go with fiber channel cards and the fiber channel connectivity. Then you might not need the 10 or 40 gig on the data side because the storage side is good to go. However, if you're using converged with like iSCSI or fiber channel over Ethernet, you may need to invest and look into some of those SFP+, SFP28, and QSFP+ environments. As I mentioned, there's a lot of things you need to be aware of, and to be honest, it takes about 5+ years to become a senior level network engineer. More so today because of how large IT has become. I mean, 15 years ago when I was coming up, it was routers, switches, and a Cisco PIX. I mean, that was kind of it. There wasn't a lot to it. Today, you have to know route, switch, firewall, DNA center, Cisco ICE, SD-WAN, Cisco ACI, and you name it. There's just so many things in networking today. I mean, there's even dedicated collaboration for voice and video, service provider content. So there's a lot when it comes to Cisco, and hopefully starting out, we'll understand a lot of the differences between the LAN campus, the LAN data center, LAN small office, home office, and remote office and business office, as well as internet connectivity when it comes to the physical layer. On to data link. So the data link layer is the start of communication between two devices on the same network. You'll learn about media access control and the logical link control for the exams, but I mean, once you learn about MAC and LLC, I have really never ever used that in my professional life. So be aware of the flow control layers. The medium access control, or MAC layer, controls how devices in a network access a medium and then gets the permission to, of course, transmit said data. Then there's LLC, or the logical link control. This identifies and encapsulates network layer protocols, controls error checking, and of course does frame synchronization. So don't take it lightly. The MAC and the LLC do a lot. Without them, a lot of our communication would not work. But what we need to worry about is the MAC address when it comes to actual switching. So we'll talk about that a little bit as well. Continuing on with the data link layer, we have the layer 2 protocol data unit, as we talked about before, called the frame. The frame contains the layer 2 address, or the MAC address. This MAC address allows two devices to communicate on a connected network. You can't communicate at layer 3 without first understanding how layer 2 works, and then you really can't understand how layer 2 works without understanding how layer 3 works. So understanding how layer 2 and layer 3 affect network communication is a really good thing to understand. The MAC address is a 48-bit hexadecimal or hex address that exists on every network device, even on virtual devices. Any device that basically connects to a network has a MAC address. And as you can see, here's an example of my MAC address. You're going to notice that in hex, each letter or number represents 4 bits. Considering we have a 48-bit hex address, each letter or number is 4 bits. Well, how many letters or numbers do we have? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because 12 times 4 is 48. Now keep in mind, hex is 0 through 9 and A through F, which technically gives us 16 possibilities. 4 bits gives us 16 possibilities. If you think back to the IP communication and subnetting, you'll know that the 4 bits represents 2, 4, 8 to 15. So 0 through 15 is 16 bits. Keep in mind the MAC and LLC layers are based on IEEE 802. Some examples of these is the 802.3 or the Ethernet standard and the 802.11 Wi-Fi standard. Keep in mind a lot of these standards have a lot of addendums to them, such as 802.11n or 802.11an or 802.11ac as a few examples. So when you're thinking about standards, there's going to be a lot to them, and when it comes to the data link layer, there can be a lot to know and learn, especially if you dive pretty deep into them. The network layer is a start of communication between two systems either on the same network or a routed or different network. Here you will focus on the IP address. Though one of the things you have to know is IPv4 and IPv6. So layer 3 PDUs are called packets. This packet contains the layer 3 address or the IP address that allows two devices to communicate on a connected or remote network. Once again, layer 3 requires layer 2 to find its next hop on the connected network. The IP address is a 32-bit decimal address that exists on every network device requiring IP communications, which today is basically everything. As an example, here is my IP address and how I access my default gateway. So if you look on the right there, this is in our connection layers, you'll see that I have an IPv4 address, a subnet mask bound to that address, I have my physical address, and I have my link local IPv6 address. So as we just saw, my IPv6 address is a 128-bit hex address that can exist on every network device as well. Keep in mind, there are two IPv6 addresses that will typically exist on every device: a link local and a configurable address. We do have entire sections and videos that will relate to IPv4 and IPv6 that you can check out. So when talking about the data link layer, broadcasting the domain, subnets, and VLANs. So what we're going to talk about here is how two devices can communicate between one another that are on different networks. So you'll see here that we have PC1 on 192.168.100.20 with a /24. We have our MAC address, and we have our default gateway of 100.1. PC2 is on the 200 network at .20. We have our MAC address for that, and we have the default gateway at 200.1. Since we don't have MAC addresses for our default gateways, we have to figure out how to find it. If PC1 wants to ping 192.168.200.20, it asks itself, is this on my local network? Well, of course, no, it's not, because 192.168.100 with a /24 and 192.168.200/24 are on different subnets. So the PC has to ask, where is my gateway? So the PC1 basically does an ARP for its gateway. I need an ARP, so who has 192.168.100.1? The default gateway, of course, sends a response saying, I do, and here is my MAC address. So once again, when your computer is talking, it gets all 7 of those layers. But at least in this case, we only get potentially 3 layers because you're doing an ARP. Layer 1, Layer 2, and Layer 3, potentially Layer 4. Once the PC gets the MAC address of the default gateway, it once again tries to send the ping to 200.20. However, you're going to notice here that the source MAC is the same as PC1, The destination MAC is the same as the gateway. That's because, once again, layer 2 is on its local network segment. The destination IP address, you'll notice, remains the same at 200.20. If you do the command arp-a, you'll be able to see all of the ARP entries that your PC has. So once the router receives the frame and packet from above, it will know the destination MAC address and will forward it on to PC2. PC2 will then go through the same process of PC1 because, well, once again, the MAC address of the default gateway for PC2 is unknown and it needs to figure it out. Keep in mind that, once again, all devices have an ARP table, but they flush those tables. So you're going to see a lot of these ARP requests going back and forth across your network because it needs to figure out who has what MAC address. The entire reason for that is because, well, IP addresses and MAC addresses can change. When we talk about DHCP entries, you'll notice that DHCP have leases. So sometimes the MAC address to IP address, or ARP, can change. And as I showed you before, looking at the connection layers, you'll see the snippet. I have my physical address, my IPv4 IP and mask, and my IPv6 address. Keep in mind at the bottom it should say IPv4 subnet mask. So yeah, moving on. Transport layer. The transport layer is the identification of the application communication between two systems. A computer and server uses ports to determine which application will respond to that communication. So you can communicate all day long based on IP and MAC address, but how do you tell which application we're talking about? So applications have to use a certain protocol, TCP and UDP, the Transmission Control Protocol, and the User Datagram Protocol. TCP is a connection-oriented protocol, which means the application needs to acknowledge the communication. This is done via 3 or more messages: SYN, SYN-ACK, and ACK, FIN, FIN-ACK, and ACK. Of course, the SYN is the synchronize, basically, which starts the communication. FIN is the finish, and then we have the acknowledgement. This creates what's called a three-way handshake. If I'm talking to you listeners out there and I send a SYN out, you send a SYN-ACK to me, and then I send an ACK to you, and then we can start our communication. This is connection-based three-way handshake communication. UDP, on the other hand, is a connectionless protocol, which means it sends the traffic, but there is no acknowledgement of that communication. If I send out UDP 53 for a DNS query, I'm going to just send it, and hopefully it reaches where it's supposed to go. Now, a lot of the times, applications like DNS have what's called a timeout. So if I say ping www.ntras.com, I'm going to wait a certain amount of time for a response to that. If I do not get a response, well, then I know the communication is bad. So there is a little bit of back and forth that goes on with UDP, but it's in a form of a timeout. So the layer 4 PDUs are called segments. Once again, segments, packets, and frames. The segment contains the layer 4 port number. I spelled here wrong, so that's cool. You may hear this called the concept of multiplexing when it comes to communications. So if I need to connect to a web server on 443, and you also need to connect to that web server on 443, well, how do we know the difference? So as we talked about before, we have source ports and destination ports. If my source port is 1030 and your source port is 1031, well, that's how the system knows they are two different connections. they'll make their response a destination of 1030 to me and 1031 to you. Moving on to the transport layer, when we talk about application addresses, if you run a netstat command in Windows, you can see what your computer is talking to from which IP address, from which port, to which IP address or name, and to which port number. So all computers, servers, phones, printers, video endpoints, whatever, they all use IP addressing, MAC addressing, and computers, once again, as well as names when it comes to DNS, to understand where they're connecting to. In this case, you'll see that my local machine is 21.6, and I'm connecting to HTTPS to like 52.159.49.199. So here we know we're connecting to a web server on that remote IP address. And then, of course, the local switches on each side make sure we have the MAC addresses of our gateways. So when it comes to network addresses, we have to cover this a little bit. We're going to go into a lot more detail into this and transport addresses in a dedicated IPv4 and IPv6 video, but for now, this is something you need to be aware of. The RFC 1918 for IPv4 has 5 classes of IP addressing. The 10 network, the 172.16 network, the 192.168 network, the 224 network, and the 240 networks. You'll notice, of course, we have a /8, a /12, and a /16, which determines the internal address space. On the right-hand side here, you'll see where the IP addresses live. 10.0.0.0 through 10.255.255.255, 172.16.0.0 through 172.31.255.255, and 192.168.0.0 through 192.168.255.255. Once again, keep in mind these are local LAN addresses, which basically means if you see any IP address within these 3 ranges, they are local to your network ranges. Anything outside of these is probably on the internet. Keep in mind, once again, these are ranges of addresses. The 8, 12, and 16 is basically the bits that can and cannot change for internal communication. 10.0.0.0/30 is a subnet of 10.0.0.0. So keep that in mind. You can subnet these as much as you want as long as they stay within the range. Now, to drive a point home, 0.0.0.0 through 255.255.255.255 is 32 bits of decimal notation, 256 in each octet, 0 through 255. IPv6 or RFC 8200 is a little bit different. You're going to notice here that we actually have 128 bits for hexadecimal. As you can see, they're all separated between colon symbols. IPv6 in and of itself is a very long video series, and it changes all the time. So originally, IPv6 was meant to remove the need for network address translation, or technically NAT overload or port address translation, which is why typically if you're in an enterprise network, you will be given maybe a /48, which will give you 48 bits of your network address, and the other 80 bits you can use for your internal subnets and hosts. So 64 bits total subnet length. That gives you, what, 16 bits of subnetting, and the other 64 bits for host addresses for each subnet. On top of IP addressing, we also have to understand ports. Once again, the transport addresses. There are a few examples here that you might want to remember. FTP, or the File Transfer Protocol, in TCP 20 and 21. A real big one is the SSH TCP protocol on port 22. Telnet on TCP 23. SMTP, or the Simple Mail Transport Protocol, on TCP 25. DNS, or the Domain Name Service, on UDP and TCP port 53. We have the DHCP server and DHCP client on UDP 67 and 68. We have HTTP on TCP port 80. Keep in mind, HTTPS is on TCP 443. SNMP on UDP 161. And syslog on UDP 514. Once again, as a kind of a refresher, TCP is a connection-based connection, and UDP is a connectionless based connection. TCP makes sure of the three-way handshake before it sends data, and UDP just sends it and waits for a timeout. So we're good on that. Kind of a mix here because, well, when you're talking about the OSI model, you do need to know about the session, presentation, and application. However, once you understand the source and destination addresses being communicated, a lot of the times the network engineer just says, I don't know anything about that, because you really don't. You need to know layer 1, layer 2, layer 3, and layer 4. If all 4 of those are good, well, it might be an application or a bug in the system. So keep that in mind as well. The session sets up or establishes the communication between systems. Opening, establishing, managing, syncing, and closing sessions. Presentations. So one of the main reasons for the OSI model is to enable coding and formatting that multiple systems can understand. The presentation layer can also facilitate encryption and decryption based on the application that is communicating. Also, certain applications may require specific presentation and coding for them to work. Again, one of the big points of the OSI model is that back when, 30, 40, 50 years ago, two computers really could not communicate between one another because they didn't speak the same language. It's like someone from Spain going to France. They're not going to be able to understand one another. However, with OSI model, we're like, okay, well, you're using AppleTalk and you're using IP. Well, we decided to use IP communications and brought that into the OSI model and said, everybody uses these set standards so everyone can communicate. Lastly, of course, is application. Basically, a coded application that runs a specific function. As an example, SMB, or Server Message Block, SSH, Secure Shell, RPC, Remote Procedural Call, RIP, the Routing Information Protocol, NTP, Network Time Protocol, and HTTP, the Hypertext Transfer Protocol, are a few applications that work at the application layer, and everything kind of rolls downhill from there. Once my HTTP server wants to present something to me, it goes from presentation to encode it. Session sets up the connection between me and the server. Transport, well, of course we know transport is 80 or transport is 443. Depending on which one you're communicating on depends on if it's secure or not. Then, of course, the IP address, MAC address, and physical layer, make sure you're hitting the right host on the right MAC address. Of course, moving on here, the Cisco exam topics, once again, for the CCNA, don't really cover these anymore. I just wanted to include them because having fundamentals and an understanding of OSI are really good for the prospective network or any type of IT engineer. And the reason for that, of course, is because interviews for a network engineer, I'm going to keep harping on that, You need to know it, you need to understand it, otherwise it's going to be really difficult to, get that job and prove, hey, I know what the OSI model is, I know how to subnet, I know what IPs are, and I know how computers can communicate, and then you move on from there. Some of these presented ideas are meant for designers, coders, engineers, physical equipment manufacturers to make a single network model for different things to communicate. Once again, I mentioned that in the last slide. If you're going to get into the programming side of things, you might really need to understand how session through application works. For CCNA and networking, 1 through 4. Now, because our first topics video on 11A and 11B is going to start in the next video series, you might want to look at some of the network devices, the routers and switches that Cisco and whomever else has available to you. On Entraz, I have an IC&D page that talks about a lot of routers and switches, firewalls and such. I need to finish getting to that. And then, of course, on Cisco.com, if you look at the products, you'll be able to see all of the plethora of products that Cisco provides. There are a lot out there. So at least try to be familiar with the different Cisco routers and different switches that Cisco has, because in terms of this course, you're going to need to know, well, how do those devices fit on the network? If we go back to our initial topics page, well, explain the role and functions of network components. What do routers do? What do layer 2 and layer 3 router switches do? And what do next-gen firewalls and IPSs do? You get the point. So, kind of a good understanding of all the layers to get you to understand the role and functions of those network equipment. So, I hope you liked the video. Once again, I'm doing a little bit of new format here, trying to figure out if I like this. I know it's a lot of wasted space, but I thought it looked cool when I was working on this last night. So, yeah, let me know in your comments below. Please be nice. And I'll see you in the next one.